All right, so let's talk about procedures. So, how do procedures work in assembly language? You read about was in MIPS, but pretty much the same stuff. Okay, or from within another procedure. So a procedure is going to get called from another procedure, and how are procedures actually represented? Well, are they something special? Do they have to be something special? What is a procedure? Let's just in general. Let's give a general definition of procedures. Okay.
Runs a calculation.
All right, potentially a calculation, but it's some code, chunk of code that hopefully is kind of reusable, right?
Yeah.
So
the main code relies on the output from that procedure.
Potentially, yeah, it might rely on, or maybe it just does something. But you're right. So the idea here is that we have a chunk of logic, and this chunk of logic needs to be used probably from multiple places, right? So as an example, and we'll write this today. As we have been going through stuff, we've seen like the sample Hello World program. I think we popped in some code where it reads something in from the user, but if we didn't, we'll do that today. But those are things like outputting something to the screen. That might be something that we want to be able to do easily from within our program, right? So we might throw that into a procedure, and whenever we need to output something to the screen, we have the procedure go ahead and call it, or the procedure go ahead and do it for us, right? As opposed to having to do all the rigmarole to make it work, where we're moving system calls into certain places and having to remember what those system calls are and all that stuff. That might be something that is kind of one of our go-to moves, output stuff to user, right? Similarly, reading something in from the user might be something we want to put into a procedure. So kind of an algorithm, a chunk of code that we want to be able to reuse. All right, so, and there's kind of a formal way of doing it in assembly through a procedure function, and we'll look at that. But really, we just need to have a way of getting to a reusable chunk of code. So you either use the straight procedure syntax, or you can use a label and just say, I want to jump to this label. So go to this part of code and do this, so it's not so much a separate part of code. In 8086, which wasn't in your reading, we kind of have two competitors for procedures. We have something called a macro and something else called a proc, a procedure. And from our example code the other day, from last class, we have our main proc, which is a procedure, and this ends that proc. All right, so this would be that that official chunk of code or whatever.
What's the other end main?
This end main would have been from actually it's extraneous. It's left over from the last thing I pasted over. So it's nothing. Although actually, if we don't have a start branch either. So it actually is not extraneous. I think if we remove it, it won't work because I think it's the end to the .code section. No, it does work. We'll skip it. So it must be from when I pasted over it. So we'll leave that alone. Because before we didn't have a procedure in here. We had the, what is it, the tiny model for it, yeah. What about parameters? Okay, so we've kind of already seen how that works when we were like staging stuff for writing something to the screen. We're reliant on our registers. So if you need to pass two things into a procedure, you kind of need to throw them into registers. Now, what's the problem with relying on registers for passing parameters? Say this again?
Limited space.
Yeah, limited space, limited registers, limited resources, whatever. We're limited, right? Also, so we'll just keep our worldview kind of small and say we have 4 registers available to us, right? Our AX, BX, CX, DX, those guys. Might those registers hold some important information right now that we don't want to overwrite? It's kind of maybe stuff that's important. All right, so tell me about the stack. we'll talk about the stack today.
Well,
Has the stack come up in your reading yet?
yes,
Yeah.
it did in his reading.
Okay. So the stack would have been an excellent answer for the procedure or parameter question, but so are registers. They both work. So tell me about the stack.
So basically, when you need to save the stuff that's in registers at that point in time, you move it to the stack, and then when it needs to get used, you pull it off the stack.
Okay, potentially. Yeah, potentially you could say I want to preserve the current state of my registers. 8086 assembly, I don't think has a catch-all preserve instruction, but certainly the newer 286 and 386 and newer Intel architecture instruction sets have a single command that just says throw everything on the stack. Now bring everything back from the stack. It has a catch-all. All right, so we don't quite have that that power tool, if you will, in 8086. But so what you're kind of indicating is we're going to still use the registers. So you want to still use the registers for our parameter passing, and use the stack to temporarily maintain what we don't want to lose from our registers, right? Okay, fair enough. How else can we handle it?
Couldn't you just put the parameters on the stack?
Yeah. I mean, if you need to pass 2 parameters to a procedure, can't you just push those 2 parameters to the top of the stack and rely on your procedure? Well, there's 2 sides of that, right? You're reliant on your procedure knowing that parameter 1 is at the top of the stack and parameter 2 is at the second to the top of the stack or something like that. But isn't the same thing true if you're loading stuff into registers? Your procedure has to know that parameter 1's in AX and parameter 2's in BX, something like that. So the same kind of stuff is true.
Isn't that the point of like the framework pointer and like the actual stack pointer to show like which ones are just saved values and then the other ones are actual values that have been pushed to the stack because we can't fit it all in them?
Sure. So the stack pointer tells us where the top of the stack is, right?
Yeah.
That's true, but it doesn't give us semantics as to what is at the top of the stack. It doesn't say that top of the stack is parameter 1 and the second element in the stack is parameter 2. It just shows us what the current top of the stack is. So we have to know that the values got pushed onto the stack in the right order. But that's no different really than remembering that parameter 1's in AX and parameter 2's in BX. It requires that kind of the same programmer wrote both pieces, or at least passed the knowledge onto the guy who's on the procedure side to know where the parameters live so he can grab them. Pretty similar to when we looked at like the hello world example where we had to stage things into those 4 registers before we actually interrupted the CPU for the operating system to take over. We were reliant on knowing that the operating system looks in AX first. Actually, for 8086, it looks in AL, but whatever. It looks in a certain register for what you're going to do. And then that what tells you where the rest of the stuff should live, right? So for the syswrite for Linux, it's, what am I going to do? That's syswrite. Where am I going to write it? That's your system output. What am I going to write and how long was it? So we required 3 parameters for that one procedure call. And those 3 parameters were staged in very specific registers. And the Linux documentation would have told us what registers we needed to put those things in. So that was information provided to us. That wasn't just us pretending or just, randomly throwing junk places until it finally worked. We had to know the 2 sides of the coin. We had to know where it was going to look before it would just work. Okay. So tell me more about this this stack. So let's talk a little bit more about the stack. So advantage of the stack is we still a limited resource, right? We don't have an unlimited size stack, but it certainly gives us some wiggle room outside of the registers, right? We have the disadvantage of it. So let's kind of get this on a slide. So let's say stack. So we'll just do pros and cons. So pros, we're going to call this guy extra memory for storing stuff. It's a benefit, right? Especially when you kind of feel confined with a limited number of registers. Okay, but coinciding with that is going to be a con that we don't really get to name the stuff that's there. It's a kind of unnamed storage. So we must remember what the value at the top of the stack means. We have to remember that whatever's at the top of the stack right now is actually this value, so that when we need that value, we can use it. All right, so we're relying on some short-term memory stuff, I guess, from the human being who's writing this. All right, but the advantage is we don't need to A, utilize our precious register resources. B, we also don't need to worry about maintaining or preserving the values of our registers. We don't have to do that extra work. Like I pointed out, in newer architectures, 286 and newer, we've had a catch-all. Just save all the registers and now copy all of them back. So they kind of promote the usage of registers versus the stack for unnamed stuff. So they have a built-in function that says take all the current registers and throw their values onto the stack. And then when you're done using the registers for whatever you're about to do, you can put back into the registers whatever was on the stack. So 2 commands, preserves and replaces. All right, so that's kind of nice in a newer architecture. But one thing I want us to do as we're kind of looking at 8086 here is, again, fall into this, just like my other classes, kind of fall into this MacGyver type of approach. We have these tools that are laid out in front of us, and we have problems we need to solve. There may be some standard ways that we might go about solving certain problems, but that doesn't mean that we can't just look at the tools and say, okay, well, how would I do this? You can change a light bulb 20 different ways. Really, I guess I'm talking about what kind of things you can stand on to get up to the light bulb, right? You can go a safe route and go with like a ladder that's stable or something like that, or you can just pile different size boxes on top of each other and hope for the best. There's different approaches to it is what I'm getting at. And they all might come out to the same result. Some might be broken clavicles or arms or stuff like that, but in any case, you're not hunting for the correct answer. You're hunting for an answer that works. All right, because we're talking to our CPU on a one-to-one basis, and chances are, even the best assembly language programmer is going to take shortcuts to make their life easier, doing things that make sense to them that isn't necessarily the most efficient, because assembly language programming is almost by definition tedious, right? So we want to make things as easy for us as possible, make it as similar to a high-level language as we possibly can in order to keep ourselves sane. All right, so a big benefit of the stack for us is that we get that flexibility of not being limited by our small number of registers. It's unnamed storage, so we might need to take a couple of notes while we're writing some of our logic to keep in mind, like, okay, well, I pushed this value onto the stack first, and I pushed this value onto the stack, so this value means this value means this, so to get this value, I need to pop it off the stack, then I pop this one off the stack, kind of keep these things together. But as long as you map it right, you remember where I put this and where I put this, you can bring your logic back together. So let's leave it at that for pros and cons. Those are kind of our two big things, the trade-off for our stack. But for us as kind of beginning assembly programmers, we want to think about this as free memory, okay, with a known way of interacting with it. So we want to take this a step further and say interacting with the stack. All right, so many of you have already had CSC300, some of you have not. But in CSC300, when we're talking about data structures, one of the data structures we introduce is the stack data structure. So tell me about stacks in general, not necessarily as it relates to assembly, but the stack data structure in and of itself.
LIFO.
Okay, last in, first out. Last in, first out. So think of it like a stack of magazines, right? So I have a magazine, I put it on top of the stack. That was the last thing I put on there. Probably it's going to be the first thing I take off because we usually don't grab from the middle of the stack or else we're asking for trouble. Things fall over, right? Okay, so the stack data structure attempts to mimic an organizational tool that we use in real life. Stacks of things, okay? Now, when we talk about the stack data structure, what are our ways of working with the stack? We have three functions available to us in the traditional way that stacks are taught to us. Go ahead.
Push, pop, and peek.
Push, pop, and peek. What's peek?
Just look at what's on top.
Okay, peek says what's at the top of the stack right now. Now, where is, back in assembly, what's up?
How come Locklear said peak is not a function of a stack?
That's fair enough. Push and pop would be, I mean, we don't have a peek in assembly language. So if we're talking about stack at the hardware level, working directly with the CPU, peek is not a known function.
Okay, so you'd have to pop it and then push it again?
Not necessarily. In fact, we'll have you guys figure it out. It was a question I was about ready to ask. How would we peek in assembly language? He pointed it out earlier, whether he realized it or not. How do I look at the top of the stack? Yeah, we have a stack pointer, SP. Tells us exactly where the top of the stack is, right? So we can just look at it. We can look at SP, which shows us top of the stack. That's peak, right? Push and pop are our manipulation functions. Getting stuff on, taking stuff off.
So you'd have to do that if you actually want to look at the value that's saved in that address, right? You'd have to push it and pop it.
Or, I mean, not necessarily. I mean, you can, I mean, we're walking through stuff here. You can look at the value of SP, which is the stack pointer. So you can look directly.
Points to the address.
You can look at the memory location of that, so we can see what's at that memory location. And when we see this the stack, I'll show it to you here in a few minutes. It shows us the mapped memory.
Okay.
It's called DMA, direct memory access. So it shows us that here's the value that lives at this point of memory, and this part of memory is preserved, protected, because it's where certain things live. So the top of our stack is going to be, our stack is contiguous memory. And, well, it actually happens to be contiguous memory. It doesn't have to be, but in architecture, it is contiguous memory. And we know where the top of it is so that we can kind of walk down. And we have a pointer, SP, which points to where the top of that stack is in memory. So that's a memory address where that guy is. So nothing keeps us from saying what value lives at the memory address contained in SP. That's just as good as popping into another register and looking at the value of that register. It's kind of the same thing. So you mentioned that push and pop, are the two things. Peek is important because we might want to know what's at the top of the stack from a problem-solving perspective. But as we just pointed out, we can certainly write a procedure that accomplishes peek. Even if we don't know about the stack pointer thing, we could just pop it off real quick, look at it, push it right back on. That's peek, right? Pop, then push. All right, so peek is look at the top of the stack. What's this?
That was just a conversation we had in class the other day.
Oh.
We were all confused about it.
Well, but I mean, does it make sense now? Yeah, so, I mean, if you're talking about it from an official level perspective, a mechanism of the stack, the stack data structure came from this idea. I mean, you don't always have to look at the top of it, but you do need to be able to get things onto the stack and get things off of the stack.
Yeah.
So pop removes from the top of the stack. Push adds to the top of the stack. And both of these guys adjust SP, which is a stack pointer. The top is now in a new place, right? So if we think about this, if you have a whole bunch of memories, let's say we have 3 things on the stack, all right? And stack pointer currently talks to the first thing. If we want to pop off the stack, which means removing the top of the stack, let's draw this picture. I'll go ahead and give myself 8 things on the stack here. And then we're going to have SP. There's SP, and we'll keep our memory addresses convenient again. There's 100. So let's say this is 100, 104, 108, 112, 116, 120, 124, 128. Okay, so those are our memory addresses. So SP currently points to the top of the stack. And let's say this is a 5, this is a 13, this is a 27, and then all these guys are unused spaces on our stack. Okay, so when we pop off the stack and we have a destination register for pop, we would be taking this 5 and loading it into something else. Okay, so effectively the top of our stack is no longer here. The top of our stack is now here. Which seems more efficient to you? Is it more efficient to move everything else up one level, or is it more efficient to make SP point to the new top of the stack? Change the pointer. Okay, so when we pop, we're grabbing the value from the top of the stack, and maybe even zeroing this out, you know, if we want to kind of reset it, but it's not really necessary. Okay, but you know, we're grabbing the value from the top of the stack, and then we're adjusting where the new top of the stack is. Make sense? So that the next time we call pop, we're not popping the same value off. We're getting the next value at the top of the stack.
We have to do that in 2 different lines of code.
We are not responsible for the SP adjustment. Pop does it.
Okay.
Yeah, and we'll see the commands here in a second.
Okay.
Okay, we'll actually see them work. But that's what pop does. When we pop something off of the stack, we get the value from the top of the stack, and we load it into whatever destination register we chose that we wanted to pop it into. And then as a side effect of that pop instruction, the top of the stack is now moved, as opposed to our entire stack being manipulated. Go ahead.
When talking about the stack, is like the lower number usually like the higher part of the stack, and then the higher number is the lower part of the stack?
Potentially. Yeah, I mean, because really these don't even need to be in order. The reason, well, so let's do a comparison between CSC300 and what we're talking about here. Stacks are introduced kind of like the second, you know, that we have linked data structures or linked lists initially in 300, right? And when we talk about linked lists, what's the advantage of a linked list over an array?
No size control.
Yeah, I mean, memory efficiency, right? Arrays require contiguous memory, so everything's right next to each other. What's good about that? Fast. Okay. Linked lists say, well, we can put one element here, the next element goes here, the next element goes down here, the next element goes way back here. They don't have to be next to each other in memory. They don't have to be contiguous. So they're memory efficient. But with that comes a trade-off in performance. They're slower. Typically, when we implement stacks, we talk about stacks in the same vein as we're talking about linked data structures. So we say that the top of the stack is here. The next element in the stack could be somewhere else in memory. It doesn't have to be right next to it. But I'm telling you that in computer architecture, it is right next to it. Why? We already said the word in the last minute. What's the advantage of having contiguous memory? Fast. So when we talk about CPUs, we're usually thinking about speed. We want things to be fast. So we're okay with saying that we now have a limited stack size, right? And we're actually structurally limited with the stack size in computer architecture, because we're saying this is our amount of memory we have. We're going to subdivide this memory into 32, if we're dealing with 8086 processors, we're going to subdivide this into 16-bit. I think it's 16 and 32. It supports both of them. but we're going to subdivide this guy into those chunks, those size chunks. And this is how many we can store at once, total stack size. All right, and what we do is we keep manipulating the pointer until it actually wraps back up to the top. So we use modulus in order to get us back to the top. But we don't have to do that math. It does it for us. So if we have 10 elements, well here I have 8. Okay, I have 8 elements in here. So this is actually, if we just take these guys, let's throw it over here. Change the color of this. This is bucket 0. This is bucket 1. We'll treat these guys like arrays. This is bucket 2, 3, 4, 5, 6, and 7. Okay, so 8 elements on our fake stack here, 0 through 7. Okay, so once we have popped, so let's see our top of our stack is currently right there, and we pop again. Well, we don't want the new top of the stack to be here, because there is no here, right? So we probably want it to go back up to the top here and hope that that value has now been released, or that we do have a limit in our fake stack here. We have a limit of 8 values that we know how to store. How do we do the math that gets us from bucket 7 back to bucket 0? So from bucket 0, I go to bucket 1. From bucket 1, I go to bucket 2. From bucket 2, I go to bucket 3. And these are offsets off of the base stack pointer. So actually the top of the stack is done with 2 registers. Base address and then an offset off the base address. But unimportant for this discussion right now. So how do I go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 0? What's the math formula that makes that work?
I feel like multiply by like the size of the int, or size of the pointer.
Say this again.
Multiply by the size of the register. Or
Don't even worry about memory addresses here. I just use normal numbers, 0 through 7. So forget about what these addresses actually are over here. This is, I want to add 1 to 0 and have it be a 1. I want to add 1 to 1 and have it be a 2. I want to add 1 to 7 and have it be a 0. How do I make that work? Okay, I use modulus, kind of like I already hinted at. Specifically, how do I use modulus? What's the math that guarantees the answer is always between 0 and 7? Well, to get a number between 0 and 7, we would mod it by what? 8. If I want a number between 0 and 9, I mod it by 10. If I want a number between 0 and 26, I mod it by 27, right? So modding it by a value gives me the remainder of an integer division. All right, so if I mod something by 10, my possible answers are 0 to 9. 10 cannot go into the value an extra time, otherwise I did the division wrong, right? You can't have 7 remainder 10 when you divide something by 10. If there's a remainder 10, the answer was actually an 8. you did the math wrong. All right, so we're probably modding by 8 here to give us a range of values between 0 and 7. Okay, and I just arbitrarily picked 8. We could have made this 17 or something like that. So I think you were confusing. You were trying to squeeze octal in there just because of the number 8. All right, so I just happened to choose 8 just because that's what the cut and paste was convenient for when I did it. So I'm modding by 8, but what am I modding by 8? Current value of the whatever the offset is, but yeah, you're right. Current value of stack pointer, as I've kind of described it on here. So if I'm at bucket 0 and I add 1 to it, now I'm at a 1. What do I get if I mod 1 by 8? How many times does 8 go into 1? 0 times with remainder 1. I add 1 to 1, I get 2. How many times does 8 go into 2? 0. With remainder 2. Now I'm at 7. How many times is 8 go into 7? 0 with remainder 7. 7 plus 1 is 8. How many times does 8 go into 8? 1 time with remainder 0. That's how we wrap back around. Make sense? So it's the offset plus 1 mod size of stack. So we'll call this guy wraparound logic. Wrap. Okay, and this is the exact same way you would implement a stack using an array. If we were to do a stack implementation in Java or something like that using arrays. Because when we build the array, we have to give it a size, right? It's like it's an 8-bucket array or it's a 30-bucket array or whatever it is. That's now our fixed stack size. So to make sure that, so we know that's the number of unique values we can store at once, but we can make sure the stack continues to logically work by keeping track at the top of the stack, always mod the size of that array. So wraparound logic is offset plus 1 mod, let's put this in parentheses, size of stack. That make sense? That keeps our wraparound logic. And it's okay to use contiguous memory for the stack on our CPU because A, we want things to be fast, so it's a reasonable trade-off. We don't need things to be unlimited because there is a trade-off. The more memory we have, the slower it's going to end up being because we have more unique places to address, right? You know, isn't it harder to get around a big city than a small city because the map is bigger? So as we're looking through the map, we have to find where we're trying to go, and there's a lot of stuff in between us and where that destination is. We can get better and better and better at reading the map. That's what's happened with modern RAM, right? So our modern memory today is way faster in terms of how fast we can reference stuff in memory than it was 15, 20 years ago, but it's also expanded. So in order to check every bucket of this, today's memory takes a lot of time relative to how long it would have taken to check a significantly smaller chunk of memory. It's probably actually, the speeds probably stayed relatively consistent. So now we can search a lot more memory in roughly the same amount of time we could have searched much less memory 20 years ago. All right, really, we might be outpacing it today actually by a little bit, so we might even be a little faster, but you get the point. Memory gets bigger. We are able to search it more quickly, but since we have more stuff to search, there's a trade-off there. We're not necessarily gaining 100% of the speed increase of whatever the faster bus is for searching for the communication channel for talking to our memory. All right, so this is our wraparound logic for the stack. Now we said that pop removes the top of the stack and adjusts SP. Push adds to the top of the stack and adjusts SP. So if my current stack pointer is here and I push something onto the stack, I'm going to push it above it. So here, well, let's just say this was a 0. I pushed a 5 on there. Then I'm going to adjust SP to give me 1 less than it used to be. All right. The reality is computer architecture, the stack is actually stored upside down. Okay, it's stored upside down, so we're always doing addition as opposed to subtraction. So the top of the stack is actually going to be, if we were looking at this like a stack, it would look like this. This is the top. We would do 2's complement subtraction to adjust the top here. But when we add to the next thing, we're going to add to the guy below it. So if I were looking at this stack, the stack would actually look like this. I have 3 values on the stack. The top is right here. To push a new value on, we'll go right there. And now that's the new top of the stack. So my stack is upside down. Make sense? Okay. So the 2 functions we use for working with the stack is push and pop. Put things onto the stack is a push. Pop, get things off of the stack. So let's see these guys work with our assembler. All right, so we have move AX 255. Let's just work with some smaller values. That's going to give us our FF. We were looking at carry flags and stuff like that last time. All right, so we'll put a 15 in there into AX. All right, and then what I'm going to do is I'm going to go ahead and I'm going to push the current value of AX. Then I'm going to move AX, comma 10. Then I'm going to pop AX. Okay, so we'll start off by throwing the number 15 into AX, which is one of our 16-bit registers in 8086. Then I'm going to go ahead and push the current value of AX onto the top of the stack. All right, we don't have to remember where the top of the stack is. SP, all that stuff is handled for us. All right, we're just going to say, I want to preserve the value that's in AX, and I want to preserve it on the stack. Which then frees us up to modify the value of AX. So we'll move into AX, the current value 10. And then we could do stuff with AX in here if we wanted to. And then we can prove we can restore the old value of AX by doing a pop into AX, which takes the current thing off the top of the stack, which we had preserved as a 15 right here, and puts it back into AX. Go ahead.
Okay. So when you're pushing 15 onto the stack and you're putting 10 into register AX, does that overwrite the 15?
It does. It overwrites the 15 that was in AX, not the stack.
Yeah.
Not the stack. And we'll see it happen. So let's walk through it one line at a time. But
Okay, so it doesn't set to 0, it just overwrites the 15.
correct. Correct. Yep. And so let's watch it happen one line at a time. Let's scooch some stuff. And let me show you the current stack. So here's our current stack right here. We currently are not showing a top of the stack because we haven't put anything onto the stack. There still should be something in SP, but whatever. Yeah, it's at memory address 100. Whatever. So, well, that's where the stack lives, and then we have the offset of it. So stack index SI is at 00, so it's gonna, current guy should be at memory address 100. All right, so we're gonna go ahead and step through this. So the very first thing we're gonna do is we're gonna move into AX, the value 15. So we should see AX up here switch to the value of 15, which is what? What value should we see in AX after this line? F, yep. All right, so there's our F. That's the hexadecimal equivalent of 15, right? All right, next thing we're gonna do is we're gonna push AX. So we're gonna take the current value of AX and we're gonna push it onto the stack. All right, AX is still F. And here's the top of my stack. It shows me that stack pointer. Okay, so we have our F right there. Make sense? All right, then we'll move into AX, the number 10. So this guy should change to a what? Somebody other than Randy. A, yep. So there's our A, because we overwrote the F with an A. Now, if we want to use AX for some mathy stuff, we can. Now, so insert 30 lines in between these two lines right here. Now we're done with AX, the new value of AX. We want to bring back the old value of AX. So we're going to go ahead and we're going to single step. There's our pop. We move the F back into AX. And notice that the top of our stack is now has been reset since we didn't have anything else on there. But we've lost that F we were preserving. It is no longer on the stack. So that's why I was letting you finish, because it's the stack that does reset, not the AX. AX is, just because we preserve the value, it's a copy, not an overwrite until we choose to overwrite it. Make sense? All right, so does that make sense how the push and pop work? Okay, and nothing keeps us from pushing multiple values. So I can come in here and I can move into AX15. I can move into BX21. I can push AX. I can push BX. Then I can move into AX10. I can move into BX2. Move BX2. I can then do add AX comma BX, which will store the result inside of AX. Then I can move CX AX, and then I can pop BX and pop AX. So let's see what all that's doing. Notice that I pushed AX first, then I pushed BX. So the value at the very top of the stack is my preserved value of BX, which is why I popped from the top of the stack back into BX first. Does that make sense? The last thing I pushed will be the first thing I should pop. Well, it will be the first thing I pop. Whether I treat it as that is going to be up to us. Because I could, this is legal. I can say pop AX, pop BX, but what I just did is I flipped the original values of AX and BX. I preserved them in one order, but when I popped them, I popped what actually used to be BX into AX, and then what used to be AX into BX. All right, so if we see that, let's go to our guy here. So we'll just keep the top of our stack up here at the top. So if we have AX's, what do we have? AX is 15 and 21. All right, so I push a 15. Okay, so that's the top of the stack. Then I push a 21. Now that guy is the top of the stack. This is the old AX value. This is the old BX value. Now I can do whatever math I want, but when I go to pop from the stack, the value I'm going to pop is the current top of the stack, which is 21. And if I want to put that back where it came from, I need to pop it into BX. That make sense? And then the new top of the stack will be here, and we saw that this guy zeroes out as we pop stuff off there. All right, so this is the new value of, this is the old value of AX. So I pop in the opposite direction than I pushed, assuming I want to put the values back where they came from. Okay? So AX is 15, BX is 21. We'll push AX, push BX. So BX, the old value of BX is at the top of the stack. So we have 21 followed by 15. Then I'll go ahead and replace AX and BX with new values. So I put a 10 into AX, I put a 2 into BX, and then I do some addy stuff, right? So I'm going to add AX and BX. This is the destination, this is the source. We're going to store the result back in AX, which is a deviation from how MIPS works, right? MIPS uses 3 registers for their arithmetic operations. What are the values and where do you want to put the answer? Okay, where Intel architecture, destination source, in this case AX is, we're doing the math with AX and BX, but we're also storing the result back in AX. That make sense? All right, so this will take the current value of AX plus the current value of BX, so 10 plus 2 is 12. Store the result back in AX, so what should the result be? What should AX be equal to after this line of code? 12 is right in decimal, but what will we see? C. Totally on purpose, not. All right, so we'll see a C in there because 12 in decimal is C in X, right? Okay. So that'll be after add, we'll store the result back in AX. Then we'll go ahead and move AX into CX because we're about to overwrite AX, right? No good reason when we're not using CX for anything. I just said, let's preserve it. We'll throw it somewhere before we overwrite it. And then we'll go ahead and pop the stuff back. Okay? But these are my backwards values when we were looking at the example. So I'm going to pop BX first, pop into BX first, which will give me what BX used to be. And then I'll pop into AX second, which is the reverse of how I pushed them. Okay? So when all is said and done, BX and AX should be 21 and 15. CX should be C. That make sense? All right. Now, what's funny about this is this looks like a whole lot of several instructions there that basically do nothing, right? It's like all that work for nothing, for that? All right, so let's walk through this. All right, so we'll move AX 15 into AX. That's going to give us our F, right? There's our F. Then we'll move our 21 into BX. Okay, there's our 15. This is the ones place. This is the 16's place. So we have 16 plus 5 is 21. That's how we got our 21. All right, we should already naturally be getting better at converting. We might not be good at it yet, but we should become more natural. Just like, who in here has had the 470 class? A couple of you, the programming language theory class. So you go into that class sucking at recursion, right? You come out of that class having trouble thinking non-recursively. Any of you experience that? Like you just want to do recursion for everything when you come out of that class, and you realize it's not always appropriate. So by the time you guys are done here, you wouldn't be able to, you'll be just giving your age in hex. Actually, that would be a good way for older people to act like they're younger.
Yeah.
Right? Is that right? No, it was good as it would be worse, right? So what's how old am I? Oh heck, how old am I? Do you know how old I am?
No.
Really? I really don't know.
What year were you born?
That's a good question. How old do you think I am? 48?
So you say
45?
or 46.
45 or 46?
Wait, no, that's not right.
It was like late 30s.
I just remember it was
My younger or older than that on the side of the room. Do I look 48? I got the balding thing going now.
You're
Yeah, I'm 38. I feel older than 38. What's I talking about? Oh, so what? So 38 in hex would be what? 22?
that makes you sound good.
Yeah. Barely drink. Just. Okay, so we have our F here, we have our 15 here for our 15 and 21 in decimal. We'll go ahead and push AX. Let's get our stack exposed here. All right, so currently we don't see the top of the stack marked in there, but we'll go ahead and step. Now we get a top of the stack. There's our F. Now we'll step again. There's the top of the stack. There's our 15. Okay, so this guy's the top. This guy's the next guy down. So notice how it's upside down, like I showed it in the slides. Okay, for the math to be fast. Not so much for the math to work out, it's for the math to be fast. Okay, then we're going to go ahead and move 10 into AX and move 2 into BX. So this should be an A and a 2. So there's our A in AX. There's our 2 in BX. Then we'll go ahead and add AX, BX, storing the result back in AX. So we should get a C in AX. Notice that BX did not change. So that add instruction didn't break BX, but we did change AX. Because that was also, it was one of the operands, but it was also the destination for the arithmetic operation. Okay, then we're going to move into CX, AX. So there's our C in CX. All right, then we'll go ahead and pop back into BX, its old value, which should be 21. Oh, I'm sorry. It should be, well, no. Oh, no, we're good. That's the top of the stack. We got it back in there. So there's our, oh no, it did come out backwards. I don't think they do reverse logic on the stack. So the next guy, well, the next guy sounds like he's going to throw a 21.
Oh, yeah. You picked a bad
Oh,
number.
oh. I get it. I just confused myself. Okay, gotcha. So it did it right, correct?
Yeah.
Okay. So, Yeah, just the conversion stuff was going crazy. All right, so we came off the stack in the order that we wanted to come off the stack. So we've put our values back in AX and BX that we started with. That is the decimal 15, which is the hexadecimal F, is in AX, and the decimal 21, which is the hexadecimal 15, in BX. And our old addition was preserved inside of CX. Now, nothing keeps us from now pushing CX onto the stack to have that be our answer. Make sense? Okay. Now, if we're going to write a procedure for adding some numbers, would it be reasonable for us to put the numbers that we want to have on the let's say we're just adding 2 numbers. For us to put the 2 numbers we want to add onto the stack, have our procedure pop those 2 numbers off, add them, and then push the result back onto the stack. So our answer is at the top of the stack. So when the procedure is done, we have gone back to where we used to be. Is that we go back to where we were previously, but now we have an addition answer inside of the stack. Does that make sense? But let's see how we walk through our code here. So let's close this. I'm going to go ahead here. Let's just gut most of this just to give ourselves some space here. So I'm going to create a second procedure. All right. So we're going to call this guy let's call it add nums. Okay. So here's our add nums procedure. And then we'll go ahead and throw in our NP add nums. All right, so this is the guy that actually adds some numbers together. And the numbers we're going to add together are the 2 numbers at the top of our stack. Does that make sense? Okay, so we need to move those numbers into some, for right now, let's do it in some registers. That way we'll kind of bump into our problem. So we're going to assume that AX and BX are currently available. All right, so I'm going to pop AX, then I'm going to pop BX, then I'm going to add AX, comma BX, then I'm going to push AX. So move our 2 numbers off the stack into registers, add them, storing the result back at AX, push the answer back into back onto the stack. So the top of our stack now has 2 elements in it, or has 1 element in it when it started with 2. We popped the 2 off, we added them together, push the result back onto the stack. Make sense? And now our procedure ends. Now we want to call this procedure from main. So we're going to say, well, you can do all lowercase, it doesn't matter. So call add nums. Now before add nums can work, what must we first do? Yeah, push some values onto the stack. So we're going to go ahead and we're going to say push. We'll do our 15 push 21. So we'll push those 2 values onto the stack. Then we'll call add nums. And then we'll go ahead and pop into AX to see our result. Make sense? All right. So 2 numbers onto the stack, call add nums. That's going to put control over here. Add nums will pop the 2 values off the stack, add them together, push the result back onto the stack because the result is going to be stored inside of AX. And then back here in main, we will pop off the stack into AX, which should be our answer. Make sense? Okay. Let's get our stack showing up here. All right, so we're going to go ahead and push 15. So there's our F. There's our 21, which is also 15. That's where we got confused last time. So F in 15, the top of the stack is 15, which is decimal 21. Then we're calling add nums, which is going to drop down here. All right, so we have deviated control of our program into the add nums procedure. So we're going to pop into AX, the top of the stack, which is going to be a, now first of all, notice this. Top of the stack is currently a 7. Seven was right here, right? Wasn't that the first line of our main procedure? Row. So when I called that procedure, it remembered on the stack the start of the procedure I had to go back to. Let's play this out. So I incorrectly got the 7, right? Now I have in my 21, my 15. So AX and BX have values in it. AX had an unexpected value in it. Then we're going to add the two of those guys together. So answer in AX is 1C. Then we're going to push 1C back onto the stack. So there's 1C at the top of the stack. Then we jump back. What did we expect to happen that didn't happen? Notice I'm hitting next step.
Or it doesn't matter.
Well, the emulator halted. These all said no op next to it. There was no operation. We expected to return here, right? But we never did. We had add nums up. We called add nums. That took control away. But we never came back. So let's stop this. Here's my emulator.
So is that the point of the jump command then?
Not necessarily, because the jump command jumps to a label.
Okay.
Yep. So it's going to be the return command. But yeah, but you're thinking the right way.
And
Yep.
the return has that return pointer.
Yep.
Register.
Yep. So have we died?
Okay.
Does stuff work?
Close it.
Well, that's what's going to happen. Is I will close it. I just wanted to see if my computer was still functional. Is that really just broken? Interesting. I really don't want to just close this. It's very nice. It's like, we're sorry, but no. So literally nothing is clickable. Can I step back multiple times? All right. No, just force quit it. Take that. Okay, well, good. So now, I'll pause this for a second. Oh. Okay, so what I put up on the, I put a link up on the, on Blackboard that is the complete 8086 instruction set. Okay, so it gives all of these, so these are all the instructions we have available to us, including this one called RET. All right, we'll look at that one here in a second. What's nice about this, so I might link to their actual website. I don't know who these people are, but the document's a nice document. So in any case, it gives you an example of pretty much every command. So if we just get down, so here's like the add command. So they show you can move into AL5, move add AL -3, and then you get your answer back. So it shows you how to call it. So add can take a register plus memory, memory plus register, register plus register, memory plus immediate, register plus immediate, whatever. And then here's an example of calling it. What we want to do is we want to go down to the call command first, all right, and understand what happened when that call command was called. Okay, so we get a procedure name. So we can call the command with a procedure name, with a label, which is similar to what you were talking about with jumps. okay? Or we can give it a 4-byte address, which is a 32-bit address. We can tell it to specifically go to a place, okay? So we can call P1, which is the name of a procedure down here. Here's our P1 procedure, which does some mathy stuff, and ultimately says return to the caller. Okay, so go back to where we came from. That makes sense? So this will get us back. Okay, but we want to understand what that value that was pushed onto the stack was. If something was thrown onto the stack that we weren't expecting. Let's go back into here. Because one thing we have to remember is just as we are using the stack for multiple things, might that stack be used by the Intel architecture for things as well? So we're competing for that resource, right? So we do need to be a little careful. We have to understand what things might get put onto the stack so that we can work with that. All right, so let's walk through this again, but we're gonna go ahead and throw a, well, I've been using lowercase for everything, so let's keep it lowercase. All right, so I'll go ahead and throw a return in there, which should then bring it back to where we left off. So the line right after this guy. Okay, let's go ahead and emulate it. Show our stack. Push, push. So there's our 2 pushes. Then we're going to call add nums. So now we're down here. We're going to pop. So that moved a 7 in here. All right. Forget about what that means for a second. So now we're going to pop off the stack into AX, pop off the stack into BX. Then we'll do some adding. So now we're down to 1C. We'll push that back onto the top of the stack. So there's 1C at the top of the stack. Second element there is that 7. Actually, the second element is not the 7, that's leftover. So actually, we only have 1 thing on the stack. We have 2 things on the stack. Here's the top of the stack, here's the second element, which is our old AX. So now we're hitting return, which should bring us back to this line. So let's go look at the return command. All the way down. So no operators, or we can give it an immediate. So what's the algorithm? So it pops from the stack our instruction pointer. So we pushed from the, what got automatically pushed to the stack was the instruction pointer, the place we need to return to. But we started screwing with the stack, right? What was left at the top of the stack? Because when we come back from this guy, it's going to pop from the stack to figure out where it needs to go back to. Well, we manipulated that, didn't we? We gave it a place that wasn't a thing. Okay? So, let's watch this play out if we don't rely on these values on the stack. So let's close this. Let's just call add nums down here, so we'll leave the stack alone. Well, it won't. I mean, I'm taking the stack. I'm going to stop using the stack.
Oh.
Yeah. So we're going to go ahead and we're going to say, let's move 15 into AX. Then we'll add AX 21, storing the result back in AX. We won't push this. All right, and let's just do this real quick. Let's do push AX, just to do something with our our stack there. All right, so the very first thing we do is call add nums. Add nums is going to move a value into AX, then it's going to do adding. All right, it's not messing with the stack at all, but we've already seen that that stack does get manipulated. It gets manipulated by this call to add nums. All right, now we want to go ahead and we want to return, which should bring us back to here. All right, so let's see this happen. Let's get our stack showing here. Oh, I need a step. So call add nums. So there's our memory address. Okay, and we're going to see how this is actually used. So then we're going to move into AX15, so there's our F. Then add AX21, there's our 24. Then we're going to return, which takes us right back up here. Okay, so how does 003 relate to 8 here? Because it came back, right? You know, if we push onto the stack, we'll see, where are we at here? There's our 24. That's the top of our stack. Forget what this is doing right now. That's we call to get to here, but it is also the next instructions, right? So this is going to happen. So if we didn't want it to happen, we would jump to a label. We could put a label after this section of code and jump to it. And we'll see that later on. But how did we get the, in this case, it was when we called here, it pushed a 3 onto the stack. And that 3 was used to get us back to the next instruction following this procedure call. Make sense? What happened? All right, so on Thursday, you're going to have a quiz. And that quiz is going to be to tell me what was that value that was pushed onto the stack? And how did we use it? Well, we saw how it got used, but what did that value represent? Because it brought us back to our code here. Make sense? It won't always be 3. It'll be something relative to how do we get back. All right? Questions, comments, concerns, bribes? All right, I'll see everybody on Thursday.